Did you know the universe is expanding? And one of the most fascinating aspects about this expansion is that it's also accelerating, growing at a faster and faster rate. Scientists like myself typically attribute this acceleration to a mysterious force known as dark energy, which we cannot directly observe. In order to understand dark energy and the behavior of the universe because of it, we turn to finding an important quantity known as the Hubble constant, which helps illustrate the rate of expansion of the universe right now. The Hubble constant, or H0, is named after the famous astronomer Edwin Hubble, whose name also features on the great Hubble Space Telescope, as well as numerous other things, including asteroids, highways, and schools. After observing certain interstellar objects appeared redder in color than they should, he used the principle of redshifting. When an object's emitted light is reddened because it moves away from the observer, to deduce that the universe was expanding. Measuring H0 has proven no easy task, however, and while numerous modern experiments and scientific collaborations have already measured the Hubble constant, these values differ vastly, particularly between those using early universe data from a few hundred of thousands of years after the Big Bang, and those using late universe data, billions of years after the Big Bang. These discrepancies in measurements are what is known as the Hubble tension. The Dark Energy Survey, DES, aims to break this tension using a novel approach independent of traditional methods that employs both gravitational waves and electromagnetic radiation. Hi, I'm Nora Sherman, a PhD candidate at the University of Michigan working on this approach. I study under the guidance of one of the leading members of the DES group that contributed to the first H0 measurement of this kind, and have worked with the Dark Energy Survey since 2018 as a college undergraduate. Together, let's explore how we use gravitational waves and electromagnetic radiation, light, to learn about our universe. Imagine sitting on the beach on a summer evening and hearing a loud noise. You can tell from the hiss and then bang that it's fireworks. But you don't know other information about it, like its color, because you didn't see it. To know that, you need to have seen its bright light. So now imagine you're sitting so you can experience the entire fireworks show. You hear the loud noise, the hiss, and then bang! And from this, you can tell if the firework was set off closer or far from where you're sitting. You see a bright light and can tell the color of the display. This is how we hope to break the Hubble tension. By listening to loud noises from distant space and finding their bright lights, we can combine distance and redshift information to calculate H0. Our loud noises are gravitational waves. Like the gentle ripples that propagate outward when a stone hits a lake, gravitational waves are ripples in space-time produced by the acceleration of objects with mass. They can traverse large distances unhindered, but are incredibly weak or incredibly quiet. Given this, Earthbound detectors can only hear gravitational waves originating from the collisions of massive interstellar objects like black holes or neutron stars. But how do we listen for these collisions? We use the ears of the LIGO-Virgo collaboration, a system of 3 gravitational wave detectors in the US and Italy. The LIGO-Virgo collaboration constantly listens for gravitational wave events occurring across outer space and alerts the astronomy community whenever they hear an event. Some of the events LIGO and Virgo hear are collisions of dead star remnants that also produce an energetic burst of bright light known as a kilonova. Kilonova occur when 2 neutron stars smash together and are also predicted for when a black hole and neutron star collide. They are much brighter than supernova explosions and only last a short amount of time before fading away. The first, and currently only sighting of a kilonova, occurred in 2017 when two distant neutron stars merged. By combining the bright light signal and the loud noise gravitational wave data provided by LIGO and Virgo, we successfully measured the Hubble constant. Our value fell perfectly in between measurements that spur the Hubble tension, but we still had one problem. The uncertainty on our value was too large for it to be significant. This is largely because we have only one data point, only one kilonova sighting. Throughout its listening campaign, the LIGO and Virgo collaboration have heard a total of 56 gravitational wave events, 14 of which contained at least one neutron star, a key ingredient to kilonova production. While DES and other experiments followed up on several of these events, looking for optical or bright light counterparts, no second kilonova was ever discovered. However, the next 5 years look to change this, with upgrades to the gravitational wave detectors that will increase their sensitivity, allowing them to hear quieter noises, as well as the 2023 start of the Legacy Survey of Space and Time at the Vera C. Rubin Observatory, which promises to gather much more optical data than our current survey. Indeed, with continued combined electromagnetic and gravitational wave follow-ups, we could see a 1% precision on H0 by 2030, and potentially relieve the Hubble tension. But why are we interested in breaking the Hubble tension with bright lights and loud noises again? By determining the true and current value of the Hubble constant, we can better understand how and the rate at which the universe is expanding right now. This offers insight into the mysterious entity dark energy, which we believe is accelerating the universe's expansion. By understanding dark energy, we can better understand how the universe will behave in the future. Will it stop growing, start shrinking, or grow on and on forever? How will it all end? By looking and listening to the collisions of massive interstellar objects, we hope to learn fundamental truths about our universe. And today, I hope you learned a little too.